So on this first day of lesson 4.6, we are going to use residuals to analyze how accurate or strong our lines of fit are. So in the last lesson, we practiced how to create a line of fit that hopefully modeled the data in the scatter plot pretty well. We did that just with a straight edge and our eyes and as using estimation, so we won't all necessarily have the exact same line of fit, but we should have a pretty good accurate line that approximates the points as accurately as possible. So how do we measure just how accurate that line of fit that we made is? Well, one way is with residuals, so that's what we're going to practice today. And when we are doing that, what we are measuring is kind of the distance or how far off the real data point was from what the line predicted. Okay, so let's go ahead and define residuals. So a residual is the difference, it's always going to be subtraction, of the y value of a data point, that's your scatter plot point originally, and then the corresponding y value found using the line of fit. A residual can be positive, negative, it can be zero. So this is what it's measuring, right? Yesterday we agreed we were not going to be connecting dots, right? When we make a trend line, we're not trying to touch every point, and probably we won't be able to. We will make a line that gets as close as possible to as many points as possible, and hopefully has a fairly even number of points above and below the line. But it is very likely that a lot of points are not going to touch the actual line of fit or trend line. So the residual is measuring how far off the real data that was collected is from what the line would have predicted for that particular X value, right? It could be a positive residual, it could be a negative residual, but it's still really marking how far off the real data point was from what the line predicts. Okay, so if you kind of understand that concept, it probably becomes natural for you to realize, okay, the smaller our residuals, the more accurate our line, right? So the smaller the residuals, that means that the scatter plot points are closer to your line. That means it's probably a stronger correlation type of problem and that the line is a good fit. So if the model is indeed a good fit, okay, then the absolute value of those residuals are relatively small, like I just said. And the residual points will be more or less likely or evenly dispersed along a horizontal axis when we graph them, because we're going to graph our residuals. Okay, if the model is not a good fit, then the residual points will form sort of wonky patterns sometimes. That's an indicator. Or if they're wildly scattered, then that means that the data just doesn't have a correlation period. So it could be that the linear model is not a good fit, or that the data itself just has no correlation at all. Okay, so let's go ahead and practice it. We're not going to do a whole lot of these. These take a little time. So I have 3 on this notes. We'll for sure do 1, maybe 2, and then maybe we'll leave the other one for class or just as extra practice. Okay, so we're going to use residuals to determine whether the model is a good fit for the data that's given in the table. In this problem, the table is showing us the weekly sales of a DVD and the number of weeks since its release. So we talked about a very similar problem. These numbers might be slightly different, but it was the same scenario. And this is our actual collected data. This is what we would make the scatter plot with right here. This is the actual sales in millions every week. Okay, then they decided that the equation y equals negative 2x plus 20 would be a good linear model for this data. We're about to confirm or deny whether that model is actually a good fit. And we're going to do that by calculating the residuals. Okay, so this is the real, if we were graphing this, this would be our actual scatter plot. This would be the points on the model, the linear model, the line of fit, the trend line, whatever you'd like to call this. It's got a lot of different synonymous names. Okay, so for example, in week 1, the actual sales were $19 million. The model predicted in week 1 that the sales would be $18 million. So this would be the point on the trend line. This is the actual scatter plot point. We always do actual subtracted from actual minus model. 19 minus 18, that's a residual of 1. So where x is 1, this is how we graph over here. This is how we graph that. So at x equals 1, the residual was 1, so that plots right here. Okay. In the next one, the actual sales were 15 million. The model predicted 16 million. 15 minus 16 is a -1. So when x was 2, our residual was -1. So here at x equals 2, I would go down to -1. That's our next residual there. Now we're going to solve this next one. On week 3, the actual sales were 13 million. For us, we're going to insert week 3 here and see what the line would have predicted. Well, -2 times 3 is -6, and -6 plus 20 is 14. So I'm going to find the difference between the actual and the model. So 13 minus 14, and that's a -1. So at week 3, we also have a residual of -1. Okay. How about this one? The actual point was 11. When we insert a 4 here as our x value, the model predicts that it would be at 12. So we'll do actual minus the model point, and that's another -1. So this residual, when at week 4, at x 1, 2, 3, at x equals 4, the residual is -1. Okay. How about for week 5? You start to get the idea here. We're going to solve what the model predicts. That's a plus sign. Sorry about that. So it's -10. In fact, that you can start to see the pattern here because it's a linear equation, right? We can see the pattern going here in our y's. And then when I do the residual here, the actual data point was 10. The model predicted 10. There is 0 residual there. Okay, landed right on top. So at x equals 5, the residual is 0. On this next one, we insert the 6. That's going to come out to 8. 8 minus 8, actual minus model, is another residual of 0. Okay. And then when we plug in week 7, that's 14, yeah, that's 6. The actual point was 7. The model predicted 6. That's a residual of +1. So when I'm over here at 7, I have a residual of +1. And then in week 8, this would be 16 minus 4. The actual was 5 million. The model predicted 4 million. That's a residual of +1. Okay, so now let's analyze our residual table, or sorry, graph, right? So in our residual table, were our points close to the x-axis? They were. Were they fairly horizontally even in displays? Well, I have 3 on top, I have 3 on the bottom, and 2 right on it. That's a pretty good model, I have to say, right? So we had just 3 points that are above 0, 3 points below, 2 right on it, that hit it right on the mark, and they're all pretty close. They're all pretty close to 0 here. They're all either -1, 0, or +1. This is a good example of a line that is a good fit to the data. Okay, so that's a residuals table. This is how you calculate it, then you graph it, and you analyze that. Okay, let's flip this over. Let's just try one more, and I'm going to go a little bit faster. I want to jump down to number 3. We're going to test our data. You can definitely go back and do number 2. We can talk about it in class. Let's jump down to this one. Okay, we have the actual data points right here. This is our model, so we're comparing the real data to this model, and we want to know, is this model a good fit for that scatter plot, basically. Okay, so let's calculate these residuals. My input is always the x value, so here is 0. So when I plug that in, I get 1. And then I subtract the actual data point from my model data point to get my residual. So at 0, the residual was +1, right there. Okay, and then I plug in a 1 here. Okay, well, that's a negative half plus 1, that's a 1/2. And then I subtract the actual data point from the model, and I get negative 1/2. So when x was 1, my residual was negative half, which is basically right here in between 0 and negative 1. Okay. Then I'm going to plug in a 2. And let's see, that's a negative 1 plus 1, that's 0. So the model predicts a 0. The actual point was a negative 3. So that comes out to negative 3. So when x was 2, our residual was a negative 3, right down here. Okay. And then you start to see the pattern happening here. That's a good way to check your work since we're going up by 1s on the x. When I do this here, I'm going to get a, that's a negative 1, that's a negative 1/2. And so I'm going to do this actual minus that negative becomes a positive. And so that's negative 4.5. So the residual at x equals 3 is 1, 2, 3, 4.5. So 1, 2, 3, 4.5 right here. Okay. And you can start to see here we're basically decreasing by half every time, which makes sense. That's our slope, right? So this next one on the model would be negative 1. Since this is going up by 1, so negative 1.5, then negative 2, then negative 2.5, and then negative 3, because we know that's the slope. As x changes by 1, we're decreasing by half. Now let's do our residuals. So negative 7 minus a negative 1 is plus 1. So that's going to give us a residual of 6. Then negative 6 minus a negative 1.5. It's going to give us that. So that's going to be negative 4.5. Then negative 4 minus a negative 2 is plus 2, so that's a negative 2. Negative 3 minus a negative becomes positive 2.5 here, so that's a negative 0.5. And then negative 1 plus 3 comes out to just a 2. And then let's finish graphing those residuals. So I had already graphed all the way here to the negative 4.5. When x is 4, 1, 2, 3, 4, the residual goes all the way down to negative 6. 1, 2, 3, 4, 5, 6. At x equals 5, the residual is negative 4.5. So 1, 2, 3, 4, 5, 1, 2, 3, 4.5. Okay. At x is 6, the residual is at negative 2. At x is 7, the residual is at negative 1/2. And at x is 8, the residual is at positive 2. So remember what we talked about. If it makes a shape, right, instead of it just kind of horizontally across, if we see a shape, if we see an abundance of points on one side or the other, if they're really far away, those are all indicators that this is not a good fit. So when I look at these residuals and I notice almost all of them are in the negative, it's making a U shape in my residual graph. And they're not, so a lot of these are pretty far off and pretty far away. The answer for this is no. This is not a good model for that, right? This equation is not a good choice for this particular problem. It is most likely that this is not linear, okay? All right, so that's all about residuals. That's how we measure how accurate when we're doing this by hand. The good news is calculators are coming and you're gonna see some really cool stuff you can do on your calculator. But for now, that's how we would calculate by hand how accurate it is. Okay, so last but not least, we're going to talk about one other topic today. It's called correlation versus causation. There's two different things here. So we've talked about correlation before, and that's anytime we notice that there is a pattern or relationship between two variables. Okay, we're going to compare that to what it means to be a causation. A causation, just flat, you know, in a nutshell, is just a lot stronger. It's a lot more of a cause and effect type of situation. So when a change in one variable causes, right, this is the biggie right here, when it directly causes a change in the other, then that's called a causation. It's a much stronger relationship. Okay, causation produces a strong association or correlation. Okay, between two variables. The converse is not true, right? So just because two things are correlated to one another doesn't mean that one is causing the other, right? So correlation doesn't imply causation. You could have two things that have a correlation with each other, but not necessarily have a causation. But you cannot, but a causation will most definitely, you know, imply a correlation for sure. Okay, so let's see if we can, you know, explore here what some of these might be, whether it's a causation or a correlation. So tell whether a correlation is likely. If so, then tell whether it's a causal relationship. So let's start with the first one. It's time spent exercising and how many calories you burned. Okay, so is there a correlation? I think we could all probably agree that yes, there probably is a correlation between how much time you spend exercising and how many calories you burn. So then we can take it a step further and say, well, is it a causation? Does exercising cause you to burn calories? Yes or no? Yeah, the answer is yes. Exercising causes you to burn calories. And so yes, not only is there a correlation, but this is causation. Okay. How about for number 5? The number of firemen fighting a fire and the size of the fire. Okay. Is there a correlation? Yes. Okay. We can expect larger fires to bring in, you know, to draw more firemen. But does one cause the other? So does the number of firemen fighting the fire cause the size of the fire to be affected? Okay. That's the question. Or like if you bring in more firemen, could you make the fire larger, right? Not necessarily, right? So there's a correlation between these, but one doesn't necessarily cause the other to happen. So this is yes to a correlation, but not causation. Okay. How about number 6 here? It says the number of times basketball player travels and the number of times the referee calls a penalty. Okay, so if you travel a lot, are they going to call more penalties? Probably. We can probably expect there to be a correlation here. Sure. Then let's ask about causation. Does traveling cause the ref to call a penalty? Does this cause the other thing to happen? Yes, actually, traveling does cause the refs to call a penalty because traveling in basketball is a penalty, right? So this does have causation. Okay. So see if you can try the next few on your own and then come back and check back. Just try a few. You can pause the video, try them, and then press play. Look at number 7. It says the number of Americans with sedentary lifestyles and obesity rates. Okay, so is there a correlation? Yes. I think all of these are probably going to have a correlation. But does sedentary lifestyle cause obesity, right? Does a sedentary lifestyle cause obesity? Well, actually, most medical community members would say that there does. So you could probably argue that this is also causation. That there's a lot of studies that have found that, you know, a big culprit of our obesity rates going up higher in this modern society is that our lifestyles are more sedentary, office jobs, we're moving less, and so forth. All right, pollution levels in the ocean and the number of oil spills. Okay, so correlation, yes. All right. Now, does the pollution level cause oil spills to happen, right? Is there a causation here? Does one cause the other? Or oil spills cause pollution levels to go up? Well, actually, if you look at it that way, you could probably say, yes, oil spills do cause pollution levels to go up. So we would say that would be causal or causation. Okay? The electricity went out for most of the day and the ice cream in the freezer melted. Okay, so that is definitely a correlation. These are all going to be correlation. But does the electricity going out cause the ice cream to melt? Yes, it does. Causation for that one. Okay, how about number 10? The number of banks in the number of banks and the population in a city. Okay, correlation, yes. Okay, does the number of banks cause the population in the city to increase? Not necessarily, right? There's probably a correlation, but one doesn't necessarily directly make the other one happen. Okay, so population doesn't cause a specific number of banks to increase and so forth, so I would say probably not a causation. Okay, so I hope you understand that difference. We'll talk a little bit more about that in class. For this last part, you're going to write 2 statements showing correlation with causation and 2 statements that have a correlation but do not have one. So be ready to discuss those in class tomorrow.